Before you begin, if you haven't watched the first video on distance, I would watch that first because we're going to be doing a slightly harder distance problem here. So now we are on the run from the police. We have decided to make a run for it. The police are still driving towards Wabash at 45 miles per hour due south. But now you are driving away from Wabash due east at 60 miles per hour. When the police are 30 miles north of Wabash and you are 40 miles east, how fast is the distance between you and the police changing? So again, we're going to split this into a moment in time on the right. We'll have a moment in time. And then we're going to have a general situation on the left. And I should say this, you've noticed we've drawn a lot of pictures. Drawing pictures is very good in related rates problems. So we're going to draw a picture of the situation. Here's Wabash again. The police are driving south and their distance is going to be given by X. But now my distance from Wabash is also changing. It's no longer a constant. So I'll call my distance Y. Then we'll say that the distance between me and Wabash is given by Z. So here's the police car. Here's me in my police car, or in my little car. Or it's you, I guess. You're driving away from the police. It's fine. And all of these things are changing over time. So we're going to have an equation relating these given by x squared plus y squared equals z squared. And to get an equation relating the rates of change, I'll use implicit differentiation to take the derivative. We'll get 2x times dx dt plus 2y times dy dt equals 2z times dz dt. I can divide both sides by 2, getting x times dx dt plus y times dy dt equals z times dz dt. So I have my related rates equation. And now I'm going to look at my moment in time. What do we have going on? Well, at this moment in time, the police are 30 miles north of Wabash. They're closing in. So x is going to be 30. Y, that's my distance. I'm now 40 miles east from Wabash. And we don't know the distance z yet. We also know that the rate of change of the police position, this distance x is shrinking by 45 miles per hour, so that's going to be negative 45. The length of y is growing. It's driving away from Wabash. So this is going to be increasing at a rate of 60 miles per hour. And we don't know the rate of change of the distance between me and the police. In fact, that's what we're trying to find out. Before we can use our related rates problem, we need to solve for z. And to do that, we're going to use the Pythagorean theorem. So we'll use that. We'll have x squared plus y squared equals z squared. Thankfully, this is a nice triangle. We'll have 30 squared, which is my x, plus 40 squared, which is my y, equals z squared. If you simplify this on the left, you're going to get 2500 equals z squared, or z equals 50. So that's nice. And with that, I can now use my related rates equation to solve for dz dt. We're going to have x, which is 30, times dx dt, which is negative 45, plus y, which is 40, times dy dt, which is 60, equals z, which is 50, times dz dt. So I have to do a little tiny bit of math here. This should be negative 135, if I'm not mistaken. Plus 60 times 40 should be 2400. That sounds about right. And actually, that's negative 1350. I forgot a 0. That sounds more correct, actually. And all that is going to equal 50 times dz dt. If I'm not mistaken, this 2400 minus 1350 should be 1050 equals 50 dz dt. I can go ahead and divide both sides by 50. This will actually be a nice number, surprisingly enough. We should get that 21 equals dz dt. So the distance is changing by 21 miles per hour. And that is how fast it is increasing. In a complete sentence, which it's usually good to do complete sentences, we would say that the distance between me and the police is increasing by 21 miles per hour. So there we go. We've used related rates to figure out how fast this distance is changing when both me and the police are both moving. So there you go.